Okay, ma'am, you can start now.
Good evening, everyone. On behalf of IEEE Census Council Hyderabad chapter and Anna University, I'll welcome you all to the another session of MEMS training program. Today's session is being conducted on the title SOI Process Techniques. We have our speaker for today. She is Dr. B.S. Shrija ma'am. She is Associate Professor at Anna University. Uh, the recording will also be available to you for referring through the session later on. I request Shrija ma'am to come and take the session.
Thank you, ma'am. Very good evening to all of you. We have been looking into this MEMS fabrication schedule and lectures for the past few months. Today, I'll be presenting you and I'll be discussing about the SOI MEMS process techniques. So as you know, this SOI MEMS process techniques has been already discussed with Sambuddha Khan in our major series. We had 5 sessions from Dr. Veda ma'am. So in that session also, this SOI process techniques have been discussed. However, we have here our people from our zone and our team, and we'll be discussing about this SOI process techniques in detail, so that those who are willing to submit fab flow or design from our zone can be benefited. Coming to this SOI MEMS process techniques, as all of you know, silicon and insulator MEMS process techniques. We are actually going for MPW, which is multi-project wafer. I've lent a few slides from Sambuddha Khan, and as you see here, it is multi-process wafer. Hope all of you can see my cursor. Are you able to see my cursor, all of you?
Yes, ma'am, we are able to see.
Yeah. So as you see here, this is a wafer. So in the wafer, we'll be placing our designs in this pattern, so that every design is a single project. So that's why we call this as multi-project wafer. So usually we have 4-inch, 6-inch. 1 second. Usually we have 4-inch wafer, 6-inch wafer, 8-inch wafer, 10-inch. So in a wafer, we'll be dividing the space as slices, which is called die, and every design will be placed in a particular place. As you see here, n number of designs will be placed on a single wafer, and that's why we call this as multi-project wafer and multi-users. Every design could be of different person from different person. So it is multi-user, multi-project. So that's why we call this as MPW. And when we go for silicon on-insulation process, it is from multi-project wafer service from Science Corporation. I have also utilized the process and the design rules from Science Corporation. So it's a highly standardized process, and we have certain design rules and certain procedures. In a better way, we may say that is a certain recipe for design. So multiple designs, we will be sharing the same design, the same wafer, and everyone can be benefited. That is the process. So I'm adopting the rules, and I'm adopting the techniques, the process from Science Corporation, and the references are also given here for much detailed reference for you later. So let me get into this SOI MEMS process techniques. So first of all, I would like to show you here, whatever I show here is a device. I want all of you to, I can see the number of participants are also very less because we have gone through several sessions, and I'm understanding that whoever is here is really looking into the design processes. So anytime if you have any doubts or difficulties, you can stop me there. We can clear it and move forward. So when you look into this design, this is a device. I want all of you to have a careful look into this device. Look at this. This is a metal. So the color code is also here. This is a 3D view of the device, and similar device, for the same device, this is the 2D cross-sectional view. Whenever a student is looking into this pictures, always they will be wondering why there is one hanging point here. So when you look into this 3D view, let me explain about this picture. So there is a metal pad here, and there is a blanket metal placed here. This orange color stands the blanket metal, and there is a yellow color which is pad metal, and this blue color is silicon, that is device layer silicon, and our device layer silicon is 25 micrometers. And the blanket metal is what we deposit as 0.65 micrometer, and pad metal height maximum is, and in between this blue color silicon and between this light blue color substrate, there is an oxide layer. That is why it is called as silicon insulator oxide. So silicon on insulator. So let me repeat, there is a 400 micrometer substrate at the bottom, and over that there is a small layer of, when you look at here, this is 400 micrometer substrate, and over that there is a small buried oxide layer of thickness 2 micrometer, and above that there is a 25 micrometer device layer which is silicon, and above that there is a metal layer, and in case there is additional layer which is blanket material, which is in between, somewhere in between the layer. Now when you look at this, there is 2 stripes here. So carefully look at this. You have to understand the devices. There is a trench here, and the device is fixed at these 2 sides. In between, I'm not sure whether it is clearly visible in the for you in the slides. So there is a trench here. There is a trench here. So this cross-sectional view is nothing but, when I just that is, there is a hole here, as you can see. When I just slice this at this particular point, remember, like a cross-sectioning this. Look at my cursor. I'm cross-sectioning this. I'm cross-sectioning this in this pattern. When I cross-section this pattern in the front view, after sectioning it, after cutting it as a cross-section, like this, what I do, look at the cursor, what I do like this. So after doing this, when I look at the front view, I will be seeing this. When I look at the front view, I will be seeing this. Since there is a trench, this part will be, for me, it will look like a hanging structure there. That's why we have this structures in the top of structure. In the 2D sectional view placed there, when we cross section it, we will not see nothing under that. So it will be seen as a hanging structure. Any doubts? You can stop me if you have any doubts. So this particular device, same thing shown here with this structural layers defined, and the design flow of the structure is, in the step 1, an SOI wafer is doped with phosphosilicate glass, PSG, on the front side. As you see here, this is our silicon substrate, and there is an oxide layer here. And over that, we have the silicon device layer. But however, when it is exposed to atmospheric oxygen, because of the reaction, there will be a thermal oxide layer at a minimal thickness formed at the bottom. And at the top, there is PSG, phosphosilicate glass, deposited. And in step 2, the glass is removed and replaced with a photoresist. So we remove the glass and we remove it with a photoresist. We can use negative photoresist as well as positive photoresist. And before going to that, I would like to mention the major steps of this process. Since it is bulk micromachining, it is lithography and what etching. Lithography substrate and then creating structures or patterns on the substrate. While creating patterns on the substrate, when it will be exposed to UV light. After exposing to UV light, it will be put in a solution for wet etching or plasma etching, which is called dry etching. So lithography and etching are two processes which are associated closely together, and those lithography and etching are the major processes of SOI MEMS techniques. Usually for MEMS technique, lithography and etching is majorly playing its role, and that is the difference with planar VLSI technology. To create moving structures, we'll be going for lithography and etching. Now, in the first step, we placed PSG, and in the second step, photoresist material is placed. And in the third step, photoresist is patterned by the light field pad metal mask. So this is where we apply the first mask. So I want you to concentrate on what I'm saying, so that it will be much clear how many masks we use and all. So here we are placing the first mask. So we will place the first mask here. This is for metal deposition, pad metal deposition. I would like to recollect that we have pad metal, blanket metal, silicon layer, substrate, and buried oxide here. So the first mask here is placed for pad metal deposition. So this is the first mask, pad metal. And over that, so a mask is nothing but a certain place will be protected and other place will be exposed. Certain place will be protected. So now without photoresist, this place is exposed and these places are covered with photoresist. So now this 20 nanometer chromium and 500 nanometer gold is deposited as the pad metal layer. So it is deposited over this. As you can see, it is deposited entirely for all the places where it comes inside, because we have created a pattern here using a pad metal mask. So here when you apply the first, excuse me, first pad metal mask, we will use the pattern what we require. For every device, the procedures and the recipe is same, and only the pattern of the device or pattern of the mask will vary accordingly. So different designs will have different patterns and different requirements. Am I audible? Okay. And now, after depositing this layer, so something called pad metal lift off. So that is the unwanted layers of the metal and the photoresist will be removed. That you can compare this step 4 and step 5 and 6. So why we put it as 5 and 6 is it is not a single step. So initially the metal will be removed and the residual of the photoresist also will be removed. So as you see here, only this metal pattern in the required place is available. So whatever I am doing is with a 2D structure. So all these are from the Science Corporation. So if this is the 3D structure, as you see here, this is a 3D, sorry. If this is a 3D structure, so from the top, we will have a mask like this. Since it is a 2D structure, it is only showing as a smaller rectangle. But when it is a 3D structure, we will have a mask which is similar to this shape from the top view. I hope it is clear. Now, that is the only part showing here, and remaining metal and the remaining photoresist is removed off. When it is going to the step 7 and 8 structure, where we place the second mask. So the first mask is the pad metal mask, where we will be creating the metal contacts as the first step. So the process of SOI MEMS, in the first step of SOI MEMS process is creating the metal contacts. So once we create the metal contact, now we will go to the next step, which is SOI mask. This is what the device layer. So now we have created mask for the device layer. So again, the photoresist is placed for coverage, and wherever we have to place the, we have to create the structure in the silicon wafer, that will be left open. I want you to recollect the 3D view, which I showed earlier. So we are going to create structure in this place. As you see here, in this place, there is a etching in the silicon. That is the blue color. The first one, wherever we have to deposit the yellow, that is pad metal. And the second one, wherever we want to deposit, we want to remove silicon. That's 25 micrometer blue color structure, silicon, wherever we have to remove that is the second step. Second mask. So we place here, as I said, there is a trench here, a small trench here. So there we have kept open, and also there is 2 slices here. There it is kept open. So now with this mask structure, photoresist is placed, mask is placed, and then UV is exposed. Then this is put into the solution. And so this part of the silicon is now, wherever we left it open, this part of the silicon is now removed. Once it is removed, again, we will be clearing it with, clear the photoresist from the residuals from the top. And now the structure is only there. The removal of this silicon is 25 micrometer. As you know, the metal deposition is 520 nanometers of chromium and 500 nanometers of gold. So that's why we do, it is a deposition. And now we have to etch 25 micrometer, as it sound smaller for us. This 25 micrometer is a big, little higher for MEMS, in case of MEMS aspect ratio. So we will be using deep reactive ion etching, which is one of the etching techniques. I want you to have a little reading for lithography and etching. So that will be more useful when you read this. Many of you would have learned, but anyway, if you do little research on lithography and etching, that will be more helpful. So deep reactive ion etching, and you will, the silicon part is removed, and also a trench in the silicon is created at this part. So remember that we now have worked only with the top layer, top silicon layer, and bottom of that there is silicon oxide of 2 micrometers. There's a silicon oxide of 2 micrometers, and there is a 400 micrometer thick bulk silicon is also available. And at the bottom there is oxide layer, automatically thermal oxide layer created. Now we have only the structure. So metal is deposited, first mask, metal is deposited, and using the second mask, we have created structures on the device layer, that is on the silicon layer. Please stop me if you have any doubts. Now, moving on to this next step, moving on to the next step. So we are going to place a shallow mask, that is silicon wafer. The content is, we are going to etch the silicon wafer from the bottom side. So when you etch the silicon wafer from the bottom side. And when you place that is shallow metal, I want you to again have a look at your the structure we have before. Look at this blanket metal. So some structures will have blanket metal and some will not have. It's depending on the designer who wish to have. If you do not have the blanket metal, you can skip the step. So that completely the design will be masked and we will move forward. So now in this particular structure, what I showed you, there is a blanket metal. So silicon wafer, we will be creating a shallow mask, and over that there is photoresist is coated, and this shallow mask, sorry, so a shallow mask will be placed on the structure. As you see here, so this is again a silicon which is created in this shape with a standing structure, because it should not sit on this top structure what we have already created. So we place a structure. For simplicity, the diagrams are shown without our device layers. So we create a simple silicon standing kind of structure. Over that, the photoresist is coated. And this particular mask, wherever we remove wherever we remove material, which is called masking. So we will place a blanket metal mask here, and then with the blanket metal mask, the structure is created. So this is actually now standing like this. That's what I said. Instead of simplicity, these parts are not drawn from step 20 to 24. So now we have a protection or a shallow mask structure placed on top of the silicon wafer, what we have created. So now this shallow mask is aligned and temporarily bonded. That is, the standing structures are temporarily bonded with this silicon wafer. And then the blanket material is deposited. As you see, there are certain places the blanket material is deposited. And this mask is to protect the metal layer. As you see here, the metal layer is protected. We are not placing the silicon on top of this metal layer because we do not want any stiction, or we do not want any the silicon layer to touch the metal layer. So to protect the metal, this mask is kept as a standing structure, and the blanket material is deposited on top of it. And after the blanket material is deposited, the shallow mask will be removed. Shallow mask will be removed. So once the shallow mask is removed, now the complete structure of ours is placed. Before that, the shallow mask is placed and the bottom side is also etched. As you see here, from the bottom side, it has been etched and there is a trench. Now the structure is a anchored structure which is fixed at both sides, and the cross-sectional view is in this form. However, the top view, if you see, I will be showing some other designed examples also at the later part of the presentation. So when you see at the 3D view, it will be anchored at 2 points. When you see a cross-sectional view, it looks like a structure, it is hanging. Any doubts in this, you can ask me. So there are 4 masks. The first mask is the pad metal mask, and the second mask is the device layer mask, and the third mask is blanket metal mask, and the fourth mask is shallow mask, which is from the bottom, which is to etch from the bottom layer, from the bottom side. The bulk material will be removed. So we call this as bulk because 400 micrometer is too thick for MEMS substrate. So that's why it is called bulk. Fine. If you understand the design flow, now let us move on to the design rules. Certain design rules to be followed while designing this SOI MEMS process. though it looks like a complicated 27-step process, it is quite actually simple in all the MEMS fabrication. Comparing to all other MEMS fabrication techniques, there are only 4 marks and 4 marks, and it is, however, the other devices, when you look into this, there will be multiple marks. So this is considered to be quite simplified structure of SOI MEMS. Now, hoping that you understood. Moving on to the next. So the design rules, the first thing is, what is the purpose of lithography in this? The lithography purpose of pad metal, silicon, substrate, buried oxide, blanket metal, and its thickness and resistivity is here. So if you look at the blanket metal, so it is useful for optical mirror substrates and substrate contacts. That's what I said. In case if we do not come across or do not need this in our design, we can skip that. The buried oxide layers, it is normally to insulate the silicon and the substrate layers. And the substrate is definitely, this is for a through-hole etching. So even sometimes the substrate mask is called as the through-hole etching mask. And silicon, this layer is the device layer. Here we will be placing the device layers. Usually remember that when you simulate all these structures also, you have to follow this dimensions. Pad metal is 0.52 micrometers. It could be plus or minus 10. I'm sorry, plus or minus 0.1. However, like it is good to maintain 0.52 micrometers. And the tolerance for the silicon layer is 0 plus or minus 1. And the substrate is 400 micrometers. So we can go for the plus or minus 5. And the buried oxide layer is actually 2 micrometer thickness. So we can have a tolerance of plus or minus 0.1. And the blanket metal is 0.65. And while simulating, you can have these resistance and resistivity mentioned, so that we might get some, we will get some good results and equivalent results, so that our device can be successfully tested according to the simulation results. Now, coming to the process rules. So as we have this blanket metal and the metal layer, there should be definitely a gap of 3 micrometers. Otherwise, it will ensure the pad metal layer is not accidentally exposed to SOI masking. While etching SOI mask, when you see here, there should be a particular amount of gap between this blanket material and this metal. And also, there should be a sufficient gap, that is minimum of 3 micrometer gap is required while you pattern the silicon structure. So it is not this one side, this side also it has to be. So wherever we place the contact metal, and when you place the second mask of metal SOI mask, there should be a sufficient space. Otherwise, the pad metal layer will also be exposed for SOI mask. So that there will be a, sometimes the pad metal will also be etched for some cases. So we have to maintain a gap there. And the next rule is, the edges of the substrate does not undermine the edge of the silicon during the trench etching process. So it should not, like when you etch from the backside trench. So this is actually called a trench, as I mentioned earlier, a complete trench in the substrate. So when you do this, we have to place like a minimum distance. Otherwise, it will undermine the edge of the silicon also. So that case, it should not happen. So we have to have a proper distance between these things. And the rule B is about the anchoring. The silicon substrate is anchored to the substrate layer. It has to be anchored through the silicon oxide. Definitely one side. As I said, when I etch these parts, there should be some anchoring maintained here. So the bottom substrate, like there should be some proper anchoring. So it should be anchored. So that should be maintained, and the minimum length of the anchor should be 10 micrometers. And then the center of the blanket metal layer is deposited with a plus or minus 35 micrometer tolerance. That is, every side it has to have minimum 35 micrometers. Otherwise, because it is also a metal, and next by that the contacts also a metal. So we need to maintain a proper distance for the blanket metal. Again, the center of the shallow mask is bonded with a plus or minus 40 micrometer tolerance. So when we do a blanket masking, there should be a plus or minus 40 micrometer tolerance. Otherwise, it will overlay on the other metal or blanket metal, whatever structure is there. So these are the major rules which we need to follow. As you see here, like pad metal layer, ensure the pad metal layer is not accidentally exposed to SOI mask, and ensure the edge of the substrate does not undermine the edge of the silicon during the trench. So we need to maintain a spacing of 50 micrometers minimally, and there should be a 10 micrometer anchoring should be there. The distance should be maintained, and plus or minus 35 micrometer tolerance to be maintained when the blanket material is deposited. When the shallow mask is bonded, then there should be a plus or minus 40 micrometer tolerance should be maintained. So these are the rules which we have to follow. Any doubts? Not able to see the chat actually. So if any doubts in the chat box, which I will, after the talk, I will be handling it. Shall I proceed? Okay. So this is the die size, chip size, which will be available, which is 11.1 chip per 11 point, that is one dice which we have as 11.15 mm into 11 point, excuse me. The allowable drawing area is 9 mm cross 9 mm. This features, that is the entire 11.5 will not be drawn. So we'll be having another tolerance of 0.5 mm, and the actual space available for us is, for drawing is 8.5 mm cross 8.5 mm. So for our team, what is available is 3 mm cross 2 mm. So we'll be leaving a 100 micrometer space here, 100 micrometer for the dicing purpose. And then we'll be placing our designs within this 3 mm cross 2 mm structure. So this shows you this it's a hyperlink actually. You can see the SOI process overview. The entire details are available in the Science Foundation Foundation website. Those are the manufacturers, vendor who will be doing this process. So defined the process, you can look into that. The application areas are inertial MEMS, inertial sensors, micromirrors, actuators, and resonators. I would like to show some simple examples for your better understanding purpose. So the first example which I am discussing here is a V-beam electrothermal actuator. And I would like to acknowledge the contributions from Dr. Preeta Nair and Dr. Joshita. So V-beam electrothermal actuator, this has been already discussed in our previous lectures also. But however, in the perspective of fabrication, I would like to show you some discussion on this. So as you know, V-beam electrothermal actuators, which works on the Joule heating mechanism. So as we know, the resistance of the sample varies with respect to the temperature. And it can be formulated using the formula. We can calculate the variation in the resistance also. And this particular structure is called a V-beam actuator, which is a very simple and commonly used actuator in microelectromechanical systems. So it has a fixed anchor here, and the blue color, this is the original place of the beams when we give an voltage to this voltage node, and this is grounded. With respect to this ground, when a voltage is applied to this voltage node, this V-beam actuator experiences the temperature and the Joule heating mechanism, and it will be enlarged. There is a deflection in the V-beam actuator, and due to the deflection and based on this arrangement of the structure, the structure is forced to move upwards. It has some elongation and it has placed in such a way it has to move upward. So it will move upward, and this acts as an actuator. So this particular mechanism is called electrothermal actuation because we are applying electrical voltage, and due to this temperature, the material is thermal material. So that's why it is called as electrothermal actuator. But however, silicon is not the temperature coefficient of silicon is not very high. Rather than, when you use polysilicon, it might be even more better. But however, when the process compliance is with silicon, we go with the silicon-based structures. So the coefficient is not very high, but it will definitely give us a deflection. So I would like to introduce a mechanism called the buckling mechanism. So it is a very simple thing. This is a beam. This is a beam, a curved beam. It is called a curved beam. So this beam, when I give a force from the top, it will come to this state. So there is only two stable states for this beam. So first stable state is the beam will be in this upward direction. And when I give a push here, it is a flexible beam, and it is designed the apex height, which is here. So which is here, the apex height and the length of the beam and the coordinates, everything is designed in such a way, when I give a push exactly here, it will come to the other state. So if the dimensions are not properly defined, then it might not come into the other stage. It might be in a different modal shapes, it can vary. But if the design is perfect, it will, when I give a push on the top, it will come to the next stage. You can imagine keeping a paper folded both the ends, little thicker paper on your hand, and when you give a push, it will come to the next state. So something similar to that. Okay. Now, what I have here is a bistable valve, which works based on the electrothermal actuation mechanism. When you look into the picture, you can understand that the V-beam actuator and the curved beam mechanism is combined together to form this particular structure. So as you see here, this is a V-beam actuator, and this is another V-beam actuator, and this is a simple curved beam, and pushing from the top will move this beam to the curved beam to the stable state 2, and it will close this particular switch. As in this case, this switch is closed and this switch is open. When I give a push from here, this switch will be closed and this switch is open. So it can act as a dual switch wherever we on particular drug delivery applications. We're not discussing about the applications here, concentrating on the fabrication part. These are anchors. These anchors are fixed. These are fixed, and there are connections here, metal contacts here. So this is a voltage node, and this is also a voltage node, and this is a ground node, and this is also a ground node. So that's how this particular bistable MEMS valve works. So these are the dimensions. So from 3 mm device to 1 mm device, we have fabricated even with different dimensions, and the fabrication Do you hear me? Am I audible? Okay. So now these are the dimensions, and we can use, as we discussed earlier, we can use any simulation, any FEM simulation tools for simulating this structures. And this is one such simulation showing the displacement, I mean, the stable state movement of the curved beam. Now the stable state has moved from the top to the bottom, second state 1 to state 2. So this has been rigorously analyzed, how much voltage is required for moving this and what is the design. Those things are analyzed, and finally we come to a conclusion of the dimensions, voltage to be given, etc. And moving on to the fabrications part. So this is the total displacement, how much it has moved. And this is about the stress distribution upon actuation. And we have to concentrate on the stress also. It has to be minimum. If the stress is higher, then there is a chance of a breakage. Even the FEM tools can show you the breakage in terms of the stress. And this is a slighter modified version of the device. Instead of having a single push here, it is a three beam actuator, three T structures, so 3T structure actuator. So based on the simple principle that the force, when the area will be less, the force will be more, so that we can get more force. This will reduce the actuation mechanism. But however, both the devices will go under the same fabrication techniques. So let us concentrate more on the fabrication mechanisms. The fabrication process flow, previously it was called as the MUMS process, but there is no more MUMS now. It is SOI process. So first the SOI wafer is taken. So it is the device 110. The orientation of the wafer is the P-type wafer with the 110. And our device, this particular device, has no shallow mask, blanket metal, so that it is only contact pad, that is pad metal mask, device layer, that is the SOI mask, and the shallow mask, that is the backside trench mask. Only 3 mask levels are there. So if any design has the blanket material, we will go for that also. So as you see here, the SOI wafer, as we discussed before, and the first step of SOI wafer is the pad metal. So as you know, like our device is, just recollect the device. The device has 4 contact layers, one here, another one here, second, third, and fourth. So these contact layers are placed here. As you see, this is our first mask level for chromium or gold deposition. Again, 20 nanometer chromium and 500 nanometer gold deposition, thickness gold deposition. So here I have shown you the top view and the cross-sectional view of the device so that you can have a better understanding. So as you see here, like look at my cursor, if I draw a line here, I cut in this pattern, and when I look into the front side, I'll be seeing this. That's why this is a cross-sectional view, and this is the view of, this is the top view. So the first mask, the second mask is my device layer. Remember the device, so the entire structure will be formed in terms of a mask layer. This will be created in, the layer will be created in the silicon substrate, that is the red color. So we placed the metal is deposited, as you can see in the figure. And secondly, the silicon is patterned. As you see, the red color is the top silicon, which is a pattern. I have used it to differentiate two silicon layers. I have used one red and one, we have used one red and one blue. So this is the layer, silicon layer, which is banded. Again, when I just cut this structure, I'll be getting a look like this. That is why it is showing this way. And the third one is from the bottom of the wafer, the top side is protected, and the bottom side mask is, we would like to have a trench. Now the pattern in the top silicon is created. From the bottom silicon, we have to do a through hole edge and create a trench. Create a trench so that we will give space for the device layer to move. Because micromechanical systems, the difference between the planar structure and the transistor structures and this MEMS devices are the movements. So to allow the device to move, we have to have this trench. So finally, look at the structure. These are anchored and trench, and you can see the white space that is completely through hole trench, and this beams can move in between layer. So this we normally called as release. Normally called as release structure. Released structure after the through hole etching, released structure is this. A detailed view of the fabrication flow, just for the understanding what we have performed, is mentioned here. So the credit goes to Indian Institute of Science because the fabrication is done there. One second. So in the process, this gives you the entire steps, like starting from the wafer cleaning, which is called Piranka cleaning. So using H2SO4 and H2O2. So how the wafer is initially cleaned. And then followed by that, the sputtering of the contacts. So chromium or gold sputtering. So here I've mentioned like what tool it has been used and what settings we have been used for, what settings have been used for doing this purpose. So however, like we are not actually going for the real-time hands-on fabrication by our side. We are anyway going to give the mask layers and those things. But however, you can just go through this, how these things are happened. So this is the sputtering. So after the sputtering, this is the second mask, device layer mask, as you can see, for our both the systems. That is the 3T head mechanism, and this is a single T head mechanism. So the lithography mask 2 for device layer. So usually this gives you how much time it is exposed, how much time is the development time, etc. Everything is mentioned here, and what a photoresist used exactly. So this is the device 2 layer mask 2 for device layer. And after the device layer silicon is etched, the structure will look like this. And then PECVD, so the IPS solution and cleaning, wafer is cleaned using IPS solution and acetone solutions. And then how this chemical vapor deposition is done for silicon dioxide. And then this is the, as I said, we do not have the third mask. Now this is the fourth mask, which is backside edge. So a simple mask, because how much place we wanted to etch in a square shape, which has been prepared. So using this RIE tool, the backside is removed. As you can see now, before release, as you can see now, the structure is, the backside is removed. And after the release, this is before release, and after the release, you can see it is a trench completely at the backside. Now this device has to move between these places so that we can have the device operations as planned. So finally, the device is, because one dicing space has not been properly given, as this is done quite number of years before. So we have broke the device and we have done some wire bonding for the characterization. As characterization is not much important now, so I'm discussing about the fabrication technique. So I'm just moving on. This is how we do the characterization, etc. And the final device looks like this. Okay. So now for your understanding, so I would like to revise once. So this is how we plan for this, nothing else. So remember, it's kind of a cooking. Like we have a particular recipe and we cannot do anything more than that. The first thing is chromium and gold metal. We can only deposit 20 micrometer and 500 20 nanometer and 500 nanometer chromium. That is the first step, pad metal mask. We can vary whatever the shapes or whatever your device, according to your device, the mask structure can vary. And the second layer is the device layer, which will be on 25 micrometer silicon layer, which is also fixed, but the structure will vary according to your design and mask. And similarly, going on to the trench side also, it's up to you. And if there is a blanket metal which can be placed. So this recipe cannot be changed at any point of time. Keeping this recipe on mind, we have to design our devices. One such device is shown here. And another device, quickly I will show you the other device also. Quickly, I will show you the other device also. It is an RF switch, dual and quad RF switch. As you see, this is a V-beam structure. Look at the structure. This is a V-beam structure. Rather than calling this as V-beam, we can also call this as H-beam. It is kind of a H structure. So that also we can call. These are the actuators. So it's quite simple. So this actuator is designed in such a way it can move up and it can move down. How much it has to move up and how much it has to move down is controlled by the voltage node and ground node, how much voltage we are giving. And again, the my acknowledgement to Dr. Preeta Nair and Dr. Joshita. And this shows the structure simulation. As you see here, the structure will move upward like this. Also, the structure will move downward like this. So the point is, when you look at this, there are contact pads kept here. So when this structure will act as only a contact. So when you see here, we have RF input port and RF output ports. So one of the port is input port and the other remaining ports are output. So when the structure moves up and touch here, it will connect this input port with this output port, input port with this output port, so that these two will also get in contact with that. So when it moves upward, it will give us 4 outputs. When it moves downwards, it will give us 2 outputs. So in that way, based on controlling the displacement upward and downward, and it will just go sit on the contact pads. That's it. It's a quite simple mechanism. So that's how this particular actuator is designed to perform as a dual and quad RF switch. So concentrating on the fabrication mechanism, as you can see here, this is how this is a cross-sectional view and top view. Again, the first mask is the pad metal mask, and this is the pad metal. And look at this, we need metal in all these parts. So the color pad metal is green color. So all these parts are we need metal. So accordingly, the pad mask is designed in such a way the pad metal is placed. So once the pad metal is placed, let's move on to the second mask. So after lifting off, it will be like this. So these are simulated using virtual prototyping IntelliFab tool. And second mask is silicon layer mask. So the entire structure has been brought in as silicon layer mask. So when we do the second mask, we get the silicon layer in this way. However, the backside is not etched, so it is still there. It is still sitting on the silicon. Now this is the trench mask. From the backside, we trench and we etch these layers so that the structure can be, the anchored structure can move upward and downward in a comfortable way. So look at the trench mask structure also. The pattern is similar. as per our requirement. So finally, this is our structure after releasing. So when you see this is actually simulated using again IntelliFab, IntelliSuite tool, and it clearly shows the release structure. And finally, if the protection layer and oxide layer has to be removed from the top and bottom, so we have this structure. And this is what the structure looks like, and this is what the fabricated image looks like. I'm not moving to the characterization, so let's first concentrate on the prototyping, or let's first concentrate on the fabrication. So the fabricated structure will look like this. So the possible SOI MEMS devices are accelerometers, gyroscopes, pressure sensors, resonators, RF MEMS switches, micro mirrors, micro relays, microfluidic devices, energy harvesters, AFM cantilevers, and microphones, optical switches, biosensors, and inertial measurement units, and micro tweezers. So these are the possible devices which can be fabricated using SOI MEMS process technology. And remember that the process technology has 4 marks. We can go for, do not think that other metals, no, only 2 metals, which are chromium and gold deposition of particular layer thickness, and then the device layer, and then the shallow, blanket metal, and then the bottom layer edge. So we have to go with these type of devices, where these are the possible applications which we can look into. So look at these structures. Some SEM images of, this is one of the resonator. Again, it is from the Science Foundry. As you see here, it will vibrate, and there are anchors. So it is fixed here, connected here using spring structures. And this entire structure is a freestanding structure which is anchored here, and it will vibrate, and this works as a resonator. And some high aspect ratio aspect ratio is nothing but how much depth we go on what thickness. So if the thickness is very small and the depth is very high, that particular the width is very low and the height is very high, then aspect ratio will be more. That is very depth structures, very deep structures. That's why we call the aspect ratios very high. This is also one of the example resonator. And as you see here, this is one of the SOI process technology structure and the IntelliSuite simulation, and the stresses, the corners, the displacement is more, because as you see here, this structure is actually simulated here, and this is a fabrication part of it. SOI process technology, and see that this is the trench, and it is allowed to move inside. There is drive electrode. No, let's not think about those things, but these are the images, examples, which I can show you. So I hope all of you are clear about how we can go for the fabrication, how we can go for the design. While designing, we have to keep these things in mind. Then we have to go for designing devices which maximum fits into this application. We cannot remember that we cannot go for other recipe or other options. Customized designs cannot be performed with this SOI process technology, where whatever I have said now. So now what we do is, in case if some of you are interested in giving me the designs, then we can fabricate it at free of cost, as we discussed earlier. So the point is, like, you have to keep these things in mind and design your structure, one thing. And after, keep the design rules also in mind. So my job here is, like, once you give the design, I will be checking the design rules completely before going for the fabrication. So as a hope all of you might have received emails. We have several certain deadlines to go ahead, as this is a global commitment. There are many people working on this, so all of them together will submit the design. As I said before in our first slide, So it is design 1 to, as Samputhakan's slide shows, it is design 1 to n, design n. So n number of designs will be fabricated together. So we need to follow the deadlines so that we can, all of us can be benefited without any delay. So once you have some design in your mind, you can simulate it and check the functionality of the design. And there will be one more class given to you, how to create the layouts and layouts which can be given to the Foundry. The layout file will be in a GDS form, as you some of you might have already know about the GDF files, but if not also, no worries, we will discuss in our next lecture. So how to create and what tools can be used for layout creation. Once our device is simulated, tested and verified and approved, we only have to create the layers and give it to the Foundry. The Foundry will do the mask and fabricate the device and give it back to us. Now, if any doubts, you can ask me. Meantime, let me just try to look into the chat box. If someone has written, you can even you can ask now if any doubts. Is there any question in the chat box? Can we have a parabolic shape of free hanging parts, ma'am? Parabolic in the planar structure is fine. That is horizontal direction. Something cannot be lifted upward. Vertically, there cannot be. We can go for planar structures or some elevations after while electrothermal actuation, it might slightly go in a set direction, but we cannot create a structure in an angular, like, because etching the device layer will be straight away etching, so there won't be any angular structures created. Cannot be. Any other questions from the participants? So if any questions, you can even type in the chat box, or else you can contact me with your questions. And I request those who are interested to submit the design so that utilize this opportunity and submit the design so that it can be fabricated. Please type your questions if you have any. All right. If no questions, we can wind up the session. Thank you for attending. And any questions? Okay. I have one. What about deposition of silicon carbide circular membrane structures? It is not possible. Silicon carbide structures cannot be created using this SOI MEMS process technology. Any other questions? So I'm ready to help you at any point. So those who are interested can submit your designs and utilize this opportunity and get a device fabricated I once again acknowledge Dr. Joshita and Dr. Preeta Nair for their contributions in these works. Thank you all for attending the lecture.
Yeah.
So meet you.
So it's done, right, ma'am? Shrija, ma'am.
Yes, ma'am.
Yeah. So, okay, so we are done with today's session. The same thing, you can go through the Census Council YouTube channel, and you can go through the session what Srija ma'am has explained today. We will be informing you when the next session will be there, and we are there to help you out throughout the training program, as ma'am has said. So thank you everyone for joining in today's session. Thank you.